This rocket has exploded on the launch pad. It has spun out of control. It has broken apart in the sky, live in front of millions of people. And yet, this same rocket might be the only thing standing between humanity and Mars. We're not talking about the moon landing. We're not talking about the space race. We're talking about something happening right now on a quiet stretch of coastline in South Texas, where engineers are trying to build the most powerful rocket ever created, one that can carry hundreds of tons into orbit, land itself back on Earth, and fly again within days. If they pull this off, the cost of reaching space could drop by more than 90%. If they don't, we may find out that getting to space was never the hard part. Every test so far has ended in failure. Engines cutting out, heat shields cracking apart, silence where there should have been signal. But those failures built toward one mission, Starship Flight 13. This isn't a routine test. This is the mission that decides whether we go to Mars or whether we stop right here, the mission that could change everything. More than half a century ago, millions of people watched as humanity reached the moon for the very first time. It was a historic achievement, one that proved impossible dreams could become reality with enough determination, engineering, and courage. But after that incredible era, something unexpected happened. Humanity became surprisingly comfortable staying close to Earth. Yes, satellites transformed communication. Space stations allowed astronauts to live in orbit for months. Robotic probes explored every corner of the solar system. Yet the one thing that was supposed to become routine, sending humans deeper into space, never truly happened. The biggest reason wasn't technology, it was cost. Every traditional rocket worked almost the same way. Engineers spent years building an incredibly complex machine, launched it once, and then watched most of it fall into the ocean or burn up in the atmosphere. Imagine buying a brand new airplane, flying it from New York to Los Angeles a single time, and throwing it away after landing. That's essentially how spaceflight operated for decades. Then SpaceX asked a dangerous question. What if rockets didn't have to be disposable? That single idea completely changed the direction of modern spaceflight. The Falcon 9 proved that first-stage boosters could return safely and fly again. What once looked like science fiction slowly became routine. Booster landings that shocked the world a few years ago are now expected after almost every launch. But Elon Musk and his engineers were never satisfied with recovering only part of the rocket. Their real ambition was far bigger. Build a launch system where both stages return to Earth, can be inspected quickly, refueled, and launched again with minimal downtime. That vision became Starship, the largest and most powerful rocket ever built. Standing nearly 400 feet tall and powered by dozens of methane-fueled Raptor engines, Starship isn't just designed to reach orbit. It's intended to carry massive cargo, deploy next-generation satellites, support NASA's future lunar missions, and eventually transport humans to Mars. It's a rocket built not just for today's missions, but for humanity's next century in space. Yet every ambitious goal comes with enormous risk. Because building the world's biggest reusable rocket is one challenge. Actually, proving it can survive launch, space, re-entry, and landing is something no one has ever accomplished before. And that's exactly why Flight 13 isn't being watched simply as another launch. It's being watched because this mission must prove that Starship can overcome the one obstacle that has defeated nearly every previous attempt. And without solving it, the dream of routine missions to the Moon and Mars could remain nothing more than an extraordinary idea. Why Flight 13 is different from every mission before it. By the time Starship Flight 13 rolled onto the launch pad, SpaceX wasn't simply preparing for another launch. It was preparing to answer a question that had been growing with every previous test. Was Starship finally becoming a reliable spacecraft? Or was it still an experimental machine learning through failure? The road to Flight 13 had been anything but smooth. Some test flights ended just minutes after liftoff. Others reached space only to lose communication during re-entry. Engines shut down unexpectedly, heat shield tiles detached under extreme temperatures. Landing attempts revealed problems that engineers couldn't fully predict using computer simulations alone. To an outside observer, those failures looked disastrous. Inside SpaceX, they were treated as data. Every explosion, every engine shutdown, and every damaged heat shield exposed weaknesses that engineers immediately went to work fixing. Instead of hiding failures, they used them to redesign hardware, improve software, and strengthen the vehicle before the next launch. That philosophy is exactly what makes Starship development different from traditional aerospace programs. Rather than spending years trying to predict every possible problem, SpaceX flies the rocket, collects real-world data, improves the design, and flies again. Flight after flight, Starship slowly evolved. The Raptor engines became more reliable, the guidance software became more precise, the launch procedures became more efficient, and perhaps most importantly, engineers gained something no simulation could ever provide: real experience. By Flight 13, the launch team had reached a point where confidence was noticeably higher than before. The massive Super Heavy booster had already demonstrated that catching and recovering enormous rocket stages was becoming increasingly realistic. Ground systems had been refined, countdown procedures had become smoother. Even weather monitoring and range safety operations had matured after numerous test campaigns. But confidence alone doesn't guarantee success, because Starship isn't judged by how beautifully it leaves Earth. It's judged by whether it survives everything that happens afterward. The launch itself lasts only a few minutes. The real examination begins once the engines fall silent, the spacecraft reaches the edge of space, and the impossible physics of orbital flight take over. Every sensor, every valve, every heat shield tile, every engine restart suddenly becomes critical. One small failure can trigger a chain reaction that ends the mission within seconds. And that's exactly why engineers weren't celebrating before Flight 13. They knew the hardest part of the mission still hadn't even begun. Getting into space was never Starship's greatest challenge. The real nightmare would begin hours later, when the spacecraft slammed back toward Earth at thousands of miles per hour, facing temperatures hot enough to melt steel, a test that no rocket of this size had ever truly mastered. The most dangerous part of the mission isn't the launch. When most people picture a rocket launch, they imagine the countdown, the deafening roar of engines, and the moment the vehicle disappears into the sky. It certainly looks dramatic, but for the engineers inside SpaceX, that's rarely the moment that keeps them awake at night, because launching Starship is only the beginning. The real danger starts after the excitement fades. Once Starship reaches space, it begins an entirely different mission. It must separate perfectly from its Super Heavy booster, maintain precise orientation, complete its planned trajectory, and prepare for one of the most brutal environments any spacecraft can experience: the journey back home. Unlike smaller spacecraft protected by compact heat shields, Starship returns as a giant stainless steel vehicle measuring nearly 400 feet from nose to booster. During re-entry, it crashes into Earth's atmosphere at hypersonic speeds, compressing the air in front of it until temperatures climb to thousands of degrees. At those temperatures, ordinary metals don't simply weaken, they melt. That's why Starship is covered with thousands of black heat shield tiles. Each one acts like a tiny piece of armor, protecting the spacecraft from an inferno hotter than volcanic lava. But here's the problem. A heat shield is only as strong as its weakest tile. If even a small section becomes damaged or falls away, the exposed steel underneath can experience temperatures it was never designed to survive. Heat begins spreading into the vehicle's structure, creating risks that grow second by second during descent. Previous flights revealed exactly how unforgiving this process could be. Engineers observed missing tiles, unexpected heating patterns, and areas where thermal protection didn't behave exactly as computer models had predicted. Those discoveries forced SpaceX to rethink more than just the tiles themselves. They refined installation methods, improved inspection techniques, upgraded onboard cameras, and even introduced new ways of monitoring the heat shield during flight. Every change was designed to answer one critical question: can Starship survive re-entry consistently enough to become truly reusable? Because if the spacecraft requires months of repairs after every mission, the dream of rapid, airline-like space travel disappears. Reusability isn't just about landing safely, it's about landing ready to fly again. And Flight 13 was expected to provide some of the most valuable data yet on whether Starship was finally moving toward that goal. But surviving the heat wasn't the only obstacle waiting in space. Even if Starship made it through re-entry, another challenge remained, one that could ultimately decide whether future missions ever reach the Moon, Mars, or anywhere beyond Earth. The challenge that could decide humanity's future in space. Even if Flight 13 completed a flawless launch, even if it survived the brutal heat of re-entry, Starship still wouldn't have solved its biggest problem. Because reaching orbit is only half the mission. The real goal has always been far more ambitious. SpaceX doesn't want Starship to simply visit space. It wants Starship to stay there, refuel, and continue its journey to destinations that have never been reachable with a single launch. Think about the distance. The Moon is nearly 240,000 miles away. Mars, even at its closest approach, sits tens of millions of miles from Earth. No rocket, no matter how powerful, can carry enough fuel to launch from Earth, reach Mars, land safely, and return home in one trip. Physics simply won't allow it. That's where SpaceX's boldest idea comes into play. Instead of launching one fully fueled spacecraft, the company plans to launch multiple Starships. One vehicle carries the crew or cargo. The others launch as orbital fuel tankers. Once in orbit, those tankers would dock with the main Starship and transfer massive amounts of supercooled liquid oxygen and methane, effectively turning Earth orbit into a giant cosmic gas station. On paper, it sounds brilliant. In reality, it's something no one has ever accomplished on this scale. Transferring cryogenic propellants in the vacuum of space is extraordinarily difficult. The fuel must remain at incredibly low temperatures. Tiny changes in pressure, temperature, or movement can affect how liquids behave in microgravity. Unlike on Earth, the fuel doesn't naturally settle at the bottom of a tank. Instead, it floats in every direction, creating engineering problems that simply don't exist inside Earth's gravity. Every pump, every valve, every connection must work almost perfectly. One failed transfer could leave an entire mission stranded in orbit. That's why engineers around the world aren't just watching starships launch. They're watching every step that brings SpaceX closer to proving these technologies can eventually work together. Because without orbital refueling, Starship remains an impressive rocket. With orbital refueling, it becomes something entirely different. It becomes a transportation system capable of opening the entire solar system. And that's the difference between building another spacecraft and building humanity's first true interplanetary vehicle. But while engineers focused on solving these impossible technical challenges, another race was unfolding behind the scenes, because SpaceX wasn't the only company, or even the only nation, determined to shape humanity's future beyond Earth. The race isn't just about SpaceX anymore. For years, SpaceX dominated the conversation about the future of space exploration. Its reusable Falcon 9 rockets transformed the launch industry, proving that rockets could land, fly again, and dramatically reduce the cost of reaching orbit. What once seemed impossible gradually became routine, but while the world watched SpaceX rewrite the rules, something else was happening. Other companies and other nations were quietly preparing their own answers. NASA is depending on Starship as the human landing system for future Artemis missions, but SpaceX isn't carrying that responsibility alone. Blue Origin is developing its own lunar lander, hoping to play a major role in returning astronauts to the moon. At the same time, governments across the globe are investing billions into next-generation launch systems, lunar infrastructure, and deep space exploration. And perhaps the most serious long-term competitor is China. Over the past few years, China's space program has advanced at an astonishing pace. From building its own space station to testing reusable rocket technologies, it has made it clear that it has no intention of watching from the sidelines. Every successful launch narrows the technology gap. Every new engine tested, every booster recovered, every mission completed, brings another player closer to competing in what many experts now call the new space race. Unlike the Cold War race of the 1960s, this competition isn't only about planting a flag. It's about controlling the future of space transportation, satellite networks, lunar resources, scientific leadership, and eventually the infrastructure that could support human life beyond Earth. That's why Starship matters far beyond SpaceX. Its success, or failure, could influence how quickly humanity expands into the solar system. If Starship succeeds, it could accelerate missions that many people expected decades from now. If it struggles, competitors gain valuable time to close the gap. But competition also creates something valuable. It forces innovation. Every breakthrough pushes everyone else to improve faster. In the end, that benefits science, exploration, and every future mission that leaves Earth. Yet despite all the attention surrounding global competition, engineers inside Starbase remained focused on something much simpler. None of those future ambitions mattered unless Flight 13 could first complete the mission directly in front of them. Because history isn't written by announcements, it's written by successful flights. As the countdown entered its final stages, millions were focused on the rocket towering above the launch pad. But almost nobody realized that the smallest components on Starship, not its giant engines, might determine whether the entire mission succeeded or ended in another spectacular failure. The mission that matters beyond today. As the final countdown approached zero, Starship Flight 13 represented far more than another rocket waiting to leave the launch pad. It represented decades of engineering, thousands of failed prototypes, millions of hours of testing, and one of the boldest ideas humanity has ever attempted. For generations, space travel has remained something extraordinary, rare, expensive, and limited to a handful of carefully planned missions. Starship is trying to change that forever. If SpaceX succeeds, future generations may look back at these early test flights the same way we look back at the Wright brothers' first airplane or Apollo 11's first steps on the moon, not because they were perfect, but because they proved a new era was possible. Of course, enormous challenges still remain. Rapid reusability must become routine. Orbital refueling has to be demonstrated. Heat shield performance must continue to improve. Future missions to the moon will need to validate technologies that have never been tested before. And one day, if everything works as planned, Starship will attempt something no spacecraft has ever done: carry the first humans toward Mars. That future is still uncertain. But uncertainty has always been part of exploration. Every great leap in human history began with a vehicle that wasn't guaranteed to succeed. Every explorer accepted the possibility of failure because the reward was far greater than the risk. Starship Flight 13 is another chapter in that same story. Whether this mission ends in complete success or reveals new problems to solve, every second of data collected moves humanity one step closer to building a transportation system capable of reaching worlds we've only imagined. The question is no longer if humanity will become a spacefaring civilization. The real question is who will solve the remaining challenges first, and how soon that future will arrive. Because one thing is already becoming clear: the age of disposable rockets is slowly coming to an end, and the era of truly reusable spaceflight has only just begun.